There are two processes of synchronization. The first one is independent process. Independent process is execution of one process does not affect execution of others process, which mean no dependencies relationship between processes and not sharing resources. The second one is cooperative process. Cooperative process is execution of one process affects execution of other process, which mean dependent on other processes and it sharing resources.
There are several problems involving critical section.
As we know, critical section is a code segment which are a shared variable. When a critical section is executing, other processes have to wait, and not all process is compulsory to enter the critical section.
A solution to critical section problem must satisfy the following three conditions.
The first one is mutual exclusion. If a process is executing in its critical section, then no other process is allowed to execute in critical section. The second one is progress. If no process is in critical section, no other process can block other processes from entering critical section. Those processes that wants to enter into critical section, it has to be allowed first. The third one is bounded waiting. When time limit is over, the process at the back will enter into critical section, and this can overcome starvation.
Let's talk about synchronization hardware.
Many systems provide a hardware support in critical section code. In synchronization hardware, uniprocessor code disable interrupt. The current running code will execute without preemption. It's generally too inefficient on multiprocessor system. Operating systems using this are not broadly scalable. There are three forms of hardware support, which are memory barriers, hardware instruction, and atomic variables.
Memory barriers is an instruction that forces any changes in memory to be propagated or made visible to all other processes. Memory model are the memory guarantees a computer architectures makes to application program. Memory models can be either 1. Strongly ordered and 2. Weakly ordered. For strongly ordered memory models, a memory modification of one processor is immediately visible to all other processes. And for weakly ordered memory models, a memory modification of one processor may not be immediately visible to all other processes. The second one is hardware instruction. Hardware instruction is either test memory word and set value or swap contents of two memory words. And the last one is atomic variables. It is non-interruptible by processor.
Mutate locks. Mutate locks is the simple one. It has acquire and release, that's it. But this solution requires busy waiting. Therefore, this pin is called spin lock. Both test and set, compare and swap can be implemented. What about semaphore?
Semaphore is an integer variable which only can be accessed via two invisible atomic, which is wait and signal. And this is to solve the problem in critical section, also to achieve process synchronization in multimedia processing environment.
Now let's talk about semaphore usage.
There are two kinds of semaphore usage. The first one is counting semaphore, and the second one, which is the better one, is binary semaphore. For counting semaphore, integer value can range over an unrestricted domain, and for binary semaphore, integer value can only range between 0 and 1. When s is equal to 1, it will enter into the critical section. When S is equal to 0, the process will exit from the critical section. Then, next process will enter into the critical section.
Okay, now is semaphore implementation. Must guarantee no two processes can be executed wait and signal at the same semaphore at the same time. This application may spend a lot of time in critical section. Therefore, this is not a good solution. If without busy waiting, it has two operations. The first one is block and the second one is wake up. For block operation, it places the process invoking the operation on the appropriate waiting queue. For wake up operation, it removes one of the processes in the waiting queue and places it in the ready queue.
Monitor.
Monitors is a high-level abstraction that provide a convenient and effective mechanism for process synchronization. In abstract data type, internal variables only accessible by code within the procedure, and only one process may be active within the monitor at a time.
Now let's talk about condition variables. Let's say we have condition X and Y, and we have two operations, which is wait and signal. If there is no wait on the variable, then it has no effect on the variable. If process P invokes signal and process Q is suspended in wait, both P and Q cannot execute in parallel. If Q is resumed, then P must wait.
There are two options available: signal and wait and signal and continue. For signal and wait, P waits until Q leaves the monitor or it waits for another condition. For signal and continue, Q waits until P either leaves the monitor or it waits for another condition.
Okay, let's talk about liveness. Liveness is a set of priorities that a system must satisfy to ensure a process making a progress. Indefinite waiting can cause liveness failure. Examples of liveness failure are deadlock, starvation, and priority inversion. For deadlock is when two or more processes are waiting indefinitely for an event that can caused by only one of the waiting process. Next is starvation. Starvation is indefinite blocking. And then priority inversion, which is a scheduling problem when lower priority process hold a lock needed by higher priority process. This can be solved via priority inheritance protocol.